Okay, let's unpack this. Foundation models, they're reshaping the AI landscape. Just amazing stuff.
Absolutely incredible. Yeah.
But, actually getting them to work across all the different places we need them, like from the tiny chip in your phone all the way up to these massive cloud clusters, that's a huge
It
challenge.
really is a massive hurdle.
And the reality often is you train a model, maybe it's a fixed size, like say 7 billion parameters,
Right.
and then you figure out, oh, wait, I actually need something maybe slightly different, maybe 10 billion or 12. But that size just, well, it doesn't exist off the shelf,
Exactly. It forces you to pick a shoe size that doesn't quite fit.
leading to compromises.
Totally. And the deployment environment for AI today is just incredibly diverse. You might need something lightning fast, real time on a mobile device, tight memory,
Hmm.
or you might have, tons of resources in a data center for huge batch jobs.
Right.
And current large models, think like the Llama 2 family, they offer a few specific sizes, right? 7B, 13B, 34B, 70B parameters.
Yeah, those discrete steps.
And crucially, each of those is typically trained completely independently from scratch.
Which means if your specific need falls between those sizes, you're kind of stuck.
Pretty much.
You either deploy a smaller model, maybe less accurate, just to hit your speed or cost
Right,
targets,
the compromise.
or you grab a bigger one and try to shrink it down later using things like quantization, pruning.
Distillation, yeah, those post hoc methods.
And here's where it gets really interesting, you were saying.
Well, yeah, because while those methods can help, they almost always need more work, like additional training or fine tuning just for the specific size or hardware you're aiming for.
Ah, okay, so it's not free.
Definitely not. It adds significant cost, complexity, time. It's not a truly flexible, sort of built in solution for adapting easily.
So we need something more fundamental, more natively elastic.
That's the idea.
And that's exactly what this fascinating paper we're diving into today offers. It's called MatFormer, the Matryoshka Transformer.
Love the name.
Right. Think of those nested Russian dolls. That's really the core concept they're using here.
It is.
So, our mission in this deep dive is to really dig into the academic side, the ingenuity behind this, understand the clever structure, the training strategy that makes this elasticity possible, and why it's such a big deal for anyone building or deploying these big models.
Yeah, let's get into it. The central academic innovation in MatFormer is putting a nested substructure right inside the standard transformer block itself.
Okay, nested.
They formalize it using this principle they call Matryoshka representation learning.
So the nesting isn't just a handy analogy, it's actually baked into the architecture. How does that work, like formally?
Yes, it's structural. So formally, they define these transformer blocks. Let's call them T. You have a sequence of them, T1, T2, T3, all the way to TG.
Right.
And the key is that the parameters of a smaller block, say T, are a perfect subset of the parameters of the next larger block, Ti plus 1.
Oh, okay.
So you can think of it like T1 is contained within T2, T2 is within T3, and so on, all the way up to the full block, TG. The smaller block's parameters are literally included in the larger one.
Just like the smaller doll fitting perfectly inside the bigger one parameter-wise? Okay. But are they doing this nesting everywhere in the transformer, like attention layers, embeddings?
Good question. Theoretically, the concept could apply elsewhere, but the paper primarily focuses on applying this nested structure to the feed-forward network block, the FFN.
Right, and that's because the FFN is where like most of the model lives parameter-wise.
Exactly that. The FFN block usually dominates both the parameter count and the computational cost, especially in large language models and vision transformers.
How much are we talking?
Often around 60% or more. Parameters, computation, a lot of it happens in those FFNs across the layers. So targeting the FFN gives you the biggest bang for your buck, basically.
Makes total sense. So, okay, how do they actually do it? Introduce this matryoshka structure into the FFN specifically.
Well, in a standard FFN layer, you've got that hidden layer with a certain number of neurons, right? Let's call it size dsteph.
Okay, Dave.
MatFormer creates this nested structure directly on those hidden neurons. For each nested size or granularity they want, say Ti, they use only the first set of neurons, like the first min neurons.
The first ones.
Yeah, so if you have M1 neurons for the smallest size, M2 for the next, up to Mg, which equals the full beef, Ti uses the first min neurons.
So the neurons for the smallest model, M1, are always the very first bunch in the full FFN layer.
Precisely. And what that means, intuitively, is those first M1 neurons get treated as the most significant. Why? Because they're included in every single one of the larger nested blocks.
They're always active no matter which size you pick later.
Exactly. The paper gives a concrete example. They use G4 granularities. And the sizes are set by ratios like 0.5, 1, 2, 4 times some base dimension. This translates to nested hidden neuron counts like DF8, D4, DF2, DF.
Okay, 4 levels of nesting.
Right. And when you stack these nested FFM blocks across all the layers of the transformer, you end up forming distinct nested submodels. M1, M2, M3, M4 in their example, M1, M2, M3, M4, MG.
Okay, wow, the nested structure itself, that's a really clever design, but how do you train one model so that all these embedded nested versions are actually, good, accurate? That seems like the really crucial academic hurdle.
It does, yeah. And that's where their training strategy comes in. And honestly, it's surprisingly elegant for what it achieves.
Okay.
Instead of some super complex joint loss trying to optimize all nested models at once, they simply train the single universal MatFormer model by randomly sampling one of the B-nested submodels at each training step.
Wait, just one at a time, not all four, however many simultaneously.
Just one per training step. So at step T, they randomly pick a granularity, say I from 1 to G.
Uh-huh.
And they calculate the standard training loss using only the parameters that correspond to that specific submodel mal.
And they just pick randomly, like uniform chance.
They primarily used uniform sampling in the paper, yeah. So each granularity gets an equal shot. They do mention you could potentially tune the probabilities for maybe minor gains, but uniform works well.
Okay, but hold on. How does training on just one submodel at a time make all the nested models good? I feel like the smaller ones might get neglected or something.
That's the really clever part. The core of the training innovation. See, unlike some older approaches, like Dynabert that tried complex joint optimization,
Right.
MatFormer's simple sampling strategy naturally leads to more gradient updates for the parameters that are shared across multiple granularities,
More updates for the shared parts.
especially those most significant neurons we talked about, the ones in the smaller models. Think about it. If you happen to sample the largest model, the parameters of M1, M2, all the way up to MG1, they also get updated, right? Because there's subsets of MG.
Okay, yeah, they're included.
And if you sample MG1, then M1 through MG2 get updated. The smallest one, M1, its parameters are part of all the granularity, so it benefits from an update every single time any of the G granularities are sampled.
Ah, I see the bias now. It's not neglecting the small ones, it's actually training them more in the sense.
Exactly. So if you have, say, G equal 4 granularities, the smallest model effectively gets trained on like 4 times as many examples in terms of parameter updates compared to the largest model.
Okay, that makes sense.
That's precisely how the paper puts it, effective training tokens. For a MADL-M with 4 granularities, they call it SMLXL, the S model effectively trains on 4X tokens, M on 3X, L on 2X, and the largest XL on X tokens, where X is the total tokens processed for that XL size.
Wow.
And this single training run, just driven by this simple random sampling, it manages to optimize the shared parameters so well that all G-nested submodels, M1 through MG, end up being accurate and performant, all nested within that single universal MatFormer model, MG.
Okay, so after this one training run, you have your main big model, MG, and you can easily pull out the explicitly trained nested models like M1, M2, etc., just by grabbing the right parameter subsets.
Yep, exactly.
But the paper talks about getting hundreds of accurate models basically for free. Where do those come from? That's not just the 4 you trained for.
Right, and that's the real breakthrough for practical deployment. It's enabled by the nested structure, plus that training method. They call it mix and match.
Mix and match? Okay.
So after training, yeah, you can easily extract the G main submodels by just using the same corresponding tie block across all the layers. Like all layer use T1 or all layers use T2. At it. But the really innovative part is, because the nesting is applied layer-wise, you can generate a combinatorially large number of additional smaller models. How? By selecting a different granularity, a different tie block for each layer independently.
Whoa, okay. Combinatorially large. How many are we actually talking about?
Well, if your MatFormer has G granularities and L layers, the theoretical number of possible combinations is G to the power of L.
G to the L.
So with their example, 4 granularities and maybe a typical 16-layer transformer, that's 4 to the power of 16 possible layer-wise combinations.
That's a staggering number. billions.
Exactly.
And these mix and match models formed by just stitching together different granularity blocks layer by layer, models that were never explicitly trained on their own, they actually work, they're accurate. That feels really counterintuitive.
It does seem wild, right? But that's genuinely one of the most fascinating empirical findings in the paper. Yes, they demonstrate that these mix and match models are highly performant. They lie right on the accuracy versus parameters trade-off curve that's defined by the main, explicitly trained granularity.
So they fill in all the gaps between the main sizes.
Perfectly. So for pretty much any given compute or parameter budget you have, you can probably find a specific combination of layer granularities using mix and match that fits it really well.
Okay, but hang on. With potentially billions of possibilities, how do you even find the best combination for your specific budget? Do you need some crazy expensive search like neural architecture search or something?
That's exactly what you would typically need to do in prior work, right? Finding optimal subnetworks within a bigger model often involve methods like NAS, which were used in things like OFA. That can be computationally heavy.
Yeah, adds cost back in.
But here's what's truly remarkable. The paper proposes a very simple heuristic, like a rule of thumb, for selecting these optimal mix-match models.
Simple how?
You basically just select granularity so that the block size gradually increases across the layers. You aim for the least slope is how they put it.
So like smaller blocks in the early layers gradually getting bigger towards the end.
Exactly, an increasing sequence of granularities across the layers. And this intuitively kind of aligns with the bias that the training method introduced favoring consistency.
And this simple heuristic, it actually works.
They show it works at least as well as, and often even better than, those expensive NAS methods for finding the best subnetwork. And it has basically zero overhead.
Wow. No extra search cost?
None. So it's this combination, the nested structure, the bias training strategy, and this super effective simple mix and match heuristic. That's really the academic heart of MatFormer's contribution.
That's incredibly practical. Okay, let's talk results. How does this actually perform in the real world? They applied it to language models first, right? MATLM.
Yep, MatLM, they built them up to 850 million parameters. And a key result is that the explicitly trained MatLM granularities, the SMLXL, they consistently outperform standard baseline transformer models trained independently at the same size.
Outperform, not just match.
Outperform. Better validation loss, better performance on one-shot downstream tasks. They mentioned, for instance, the 850M MatLM shows a significant 0.01 log perplexity gap over Dynabert. That's a noticeable improvement in how well the model predicts text.
Okay, that's impressive for the main models and the mixed match ones. Do they actually fill those performance gaps nicely?
Absolutely. They perform exactly as promised in the paper. They beautifully fill in that accuracy versus parameters curve, sitting right on the trade-off line traced by the SMLXL points. So you genuinely gain access to potentially hundreds of accurate models covering a whole range of sizes, all from that one initial training run.
That's the free model of promise delivered.
Pretty much.
Do these MatLMs scale okay? Like, do they follow the usual scaling laws we expect from large models?
Yes, that's another important check they did. The paper confirms MatLM scale reliably. Across different sizes, different granularities, they follow similar laws versus compute laws as standard vanilla transformers. That suggests the fundamental architecture is sound and holds up as you make them bigger.
Okay, good. Now, something you mentioned earlier, consistency. How consistent are the outputs of, say, the small MatLM compared to the big XL one? You said that's vital.
Absolutely vital, yeah. Especially for deployment optimizations. And the paper shows MatLM submodels have highly consistent behavior with the universal MatLM XL model. They measured it using things like exact match and KL divergence.
KL divergence, measuring the difference in output probabilities.
Right. Lower KL means more similar behavior, and they found MatOMs were up to 11.5% more consistent than corresponding baseline models. That higher consistency is a direct benefit of the shared parameters and that bias training we discussed.
That consistency sounds really powerful for dynamic deployment scenarios. What about vision? Did it work for images too? MatVenti?
It did. They successfully applied MatFormer to vision transformers, creating MatVit models.
And the performance?
On standard benchmarks like ImageNet 1K classification, the MatVit models matched or even slightly outperformed standard VTs of comparable size. MatVit L16, for example, was up to 0.35% more accurate.
Okay, so parity or better.
And crucially, yes, the mixed match capability works just as well for vision. You get the same elastic accuracy benefits, letting you pick a MatFit submodel perfectly tailored to your image processing budget or latency needs.
Nice.
And connecting this to the bigger picture, a really key application they highlight for MatFit is enabling elastic encoders for adaptive image retrieval.
Okay, what does that mean? Adaptive image retrieval.
Well, you know how vision transformers learn a kind of metric space for images, which helps find similar ones.
Uh-huh.
They showed that this crucial metric space structure is actually preserved across the nested MatVit submodels. The small models understand similarity in roughly the same way as the big one.
Ah, okay. So what does that preservation mean in practice for image retrieval?
It's a big deal. It means you can use a smaller, much faster MatVit submodel to encode your query image the way you're searching with.
Right, process the query quickly.
Exactly. While the potentially massive database of images can be encoded just once using the larger universal MatVit model. And because that metric space structure is consistent, the retrieval accuracy stays high even though you use different model sizes for the query in the database.
That sounds really efficient.
It is. They showed you could cut the compute needed for the query by over 40% with less than a 0.5% drop in retrieval accuracy. That's a huge practical win for building large-scale image search systems.
Wow. Okay, so bringing it all together, how does MatFormer really change the game for deployment? Flexibility, speed?
Well, it's designed with both static and dynamic workloads in mind. For static needs where, your compute budget up front, you just use mix and match after training. Find the most accurate submodel for that specific budget.
Right.
You could effectively deploy a model equivalent to, say, a 40 billion parameter baseline, but you got it with zero additional training FLOPs compared to training it from scratch. That's a massive efficiency gain right there.
Zero additional training cost for hundreds of accurate models. That's pretty hard to beat.
It really is. And then for dynamic needs, maybe your compute resources fluctuate or the difficulty of the input changes moment to moment.
Yeah.
You can actually extract the optimal submodel on the fly at inference time from that single universal MatFormer model you already have loaded.
Dynamically switching sizes.
Potentially, yeah. And that high behavioral consistency we talked about is key there. It means when you switch between submodels, the predictions don't suddenly jump around wildly. It minimizes that drift. Okay. Plus, they mentioned the nested structure itself might help with things like memory-efficient model collocation, maybe making it easier to load and switch between different submodels on the same hardware.
And you mentioned it helps with advanced stuff too, like speculative decoding for language models.
Exactly, that high consistency again. Using a consistent MATLMS, small as the draft model and the XL extra large as the verifier, they found it could be up to 6% faster than using two independent baseline models for speculative decoding.
Why faster?
Two reasons, really. Partly the consistency itself just makes the process more efficient, but also because it's all one universal MatFormer model, there's potential to leverage a shared attention cache between the draft and verifier XL models during the coding. You can't do that if you're using two totally separate baseline models.
Ah, interesting technical benefit there too. Okay, so summing it all up, what's the big takeaway here?
MatFormer looks like a really significant step both academically and practically. It's introducing this novel, natively elastic transformer architecture built around a conceptually simple but really powerful nested structure, mainly in that FFM block.
Right, and the training is key.
Precisely. That clever sampling strategy during training just perfectly leverages the nested structure. It lets you pull out potentially hundreds of accurate submodels from just one training run, basically for zero extra cost, all thanks to that mix-match idea.
And it works across the board, language, vision.
Yeah, it seems to generalize beautifully. Language, vision, different model types like encoders, decoders, and it still follows those reliable scaling behaviors we expect.
So the ultimate result is just way more flexibility.
Exactly. Unprecedented flexibility in deploying foundation models. You can tailor them almost perfectly to whatever constraints you have without all the usual retraining headaches and costs. It unlocks faster inference, enables cool adaptive applications like that image retrieval example.
It really is like having that whole set of perfectly fitting Russian dolls, right? All the different sizes, ready to go just from training the biggest one once. It feels like it fundamentally changes the train once, deploy many ways paradigm.
Yeah, it definitely shifts the focus from training lots of separate discrete models to training a single, highly adaptable, universal model that contains all those possibilities within it.
Okay, so here's a final thought to chew on. If one universal model can so efficiently contain and give us access to hundreds of accurate submodels of all these different sizes, what does that imply for how we might design AI hardware in the future?
Interesting question.
Could we maybe build chips that are specifically optimized to exploit this kind of nested structure, chips that could seamlessly, maybe almost instantly switch between these different granularities right at the hardware level? Imagine the efficiency and adaptability that could unlock.